So here we're going to see if these triangles are congruent, and if so, we're going to state the theorem that proves it. So let's take a look. We've got P, Q, R. We're trying to compare that to S, T, W. All right, and it looks like we have a side angle side scenario going on. And we can say that 1 is in the same position, 2 looks to be in the same position. It's between my double line and my unnamed line. 3 is between my single line and my no-name line for both of them. So yeah, we would say that these are congruent by side angle side. This one right here is a little bit tricky. Okay, we've got M, A, T, and we're trying to compare it to M, H, T. And looking at it right away, we want to say that these sides are obviously going to be congruent because they're shared between MAT and MHT. However, if I pay very close attention, I know that MA is congruent to AT, and I know that MH is congruent to HT. But I don't know that MA is congruent to MH, okay? I don't know about this, and I don't know about AT being congruent to HT. So while it looks like it should be a side-side-side situation, I don't have that correct information available to me. So based on the information I have, I cannot say that they are congruent. We don't have enough information. Okay, so make sure you're paying attention to those lines and confirming, because in this situation, they are actually not congruent. Up here, it asks what else is needed to prove these triangles congruent by angle, side, angle. So if I'm looking for angle, side, angle, I have those matched over here on this left side for my side and my angle. What I need is for T to be congruent to R. So if this is going to work, angle T must equal 40 degrees for angle, side, angle congruence. I've got angle W, I've got the side. I've just got to find that angle that makes 8 the included side, because we do know that this needs to be the included side. So if T is equal to 40, then we're good to go. But we've got to make sure that we have that. And then this last one, determine if the triangles have side-side-side congruence. So we can look at ABC. We know it's 1, 2, 3. AC is 1, 2, 3, 4, 5, 6, 7. If I look down here, I've got 1, 2, 3 for DE, 1, 2, 3, 4, 5, 6, 7. And so I have two sides right here. These are triangles. These do look to be right triangles based on the coordinate grid. So I do have Pythagorean theorem. Okay, so I'm actually going to write this out. We've got BC squared equals 3 squared plus 7 squared. And I also have 3 squared plus 7 squared equaling EF squared. And if I have that, if you're paying attention, 3 squared plus 7 squared is equal to 3 squared plus 7 squared. So I'm going to do this the long way, but some of you guys might see this already. 3 squared plus 7 squared equals both EF squared and BC squared. So if that's the case, all three of these things equal each other, so I can remove this piece. I don't even need it anymore. I won't cross them out, but I don't need them anymore. I can just say that BC squared equals EF squared, and if that's the case, then I can say BC is equal to EF, because I would square root both of these. And if BC equals EF, then I have congruence by side, side, side.